We have reached another major milestone in this course. Where are we placed currently? We have looked at the functionality needed to make two nodes communicate. At the physical layer, you needed encoding. At the link layer, you needed framing, error recovery, and reliable transfer for this. But how useful is a two-node network? Not much. So we moved on to using this particular framework to interconnect a few hundred nodes. In this context, at the link layer, we looked at the different types of topology as well as the media access control that is needed for these nodes to access the media for communication. So in this context, we saw that there were certain restrictions in expanding the span of the network. For example, in Ethernet, it says you cannot go beyond a few hundred meters depending upon the technology, and you cannot have more than 1024 hosts, and even in token ring you cannot have more than 250 hosts. What if we want even bigger networks with thousands of nodes? Switching is the solution to this. We have briefly covered this before. Also notice that I haven't said millions of nodes. We will get there eventually. So here is the outline of this video. I will explain the switching concept first. And there are two types of switching, circuit and packet switching. So we will cover these next. Internet predominantly uses packet switching, and there are different types of packet switchings. This aspect will be covered in another video. We have covered this before. A switch is nothing but a multi-input, multi-output device whose main function is to move packets or frames from one input to another output. This provides a star topology. This makes the switching architecture very scalable. Not only that, for a given interface or a link, it runs appropriate data link protocols. This figure explains the same thing better. So we have three different networks, Ethernet, Ethernet and token ring, interconnected through a switch. This switch has three interfaces, but the way I have represented here is each interface I am representing with an input as well as output. So you can get packets from it as well as send packets out on it, but I have separated out as input ports as well as the output ports. A switch provides a star topology. This is obvious in that this is the switch and I'm interconnecting with Ethernet 1, interconnecting with Ethernet 2 and interconnecting token ring 1. So as you can see, this is a star topology. An important point to note here is that the switch is very different from a hub. Hub is a physical layer thing that just takes signals and puts the signals on the output link. There is no buffering involved or any data link protocol being employed as part of the hub. Whereas in a switch, you actually retrieve the entire packet, store it here in the form of a buffer, and then when you are transferring it onto this other link, you employ the media access control that is part of this link before you can transfer that particular packet on this link. In other words, when you're trying to send the packet, if you see that the channel is busy, since Ethernet employs CSMA, you need to wait till the channel becomes idle before you can transfer the particular packet. Naturally, when you're switching packets from an input to output and you have multiple output ports, the question there is which port would you put an incoming packet on? So that's an important functionality a switch has to handle, and we will see more of it in the upcoming videos. A few points to note. Switching is a concept and there are different types of switching, circuit and packet. Since it is a concept, you can find its use at different layers. So it's possible to do switching at the link layer as well as the network layer. We will focus predominantly on packet switching since this is the core of the internet. The devices that employ packet switching at the link layer are called bridges or switches. Layer 2 switches typically, and when you employ switching at the network layer, the devices that do that are called routers. The switching didn't quite arise in the context of interconnecting LAN segments like Ethernet as portrayed in the example. In fact, its origins are rather old in the telephone networks. This was in 1890s. At that time, the need was to establish a line between two telephones, so these switches were used, and the process was manual. In fact, there was these telephone operators, so when you make a phone call, they used to plug in these wires by talking with each other, thereby establishing a line between the two telephones. Manual, as you can see, can be rather tedious. Automatic is better, and there's an interesting story on how this move from manual to automatic happened. So there was this person, Strauger, who was an undertaker, and in his town there were two undertakers. It so happened that his competitor's wife was a telephone operator. So the Strauger felt that his competitor's wife was directing all the telephone calls to her husband, and he felt there was something that needs to be done about it, and thereby he went about and invented automatic switching. So initial switching at the time was electromagnetic. Slowly this went on to electronics switching. Circuit switching involves two phases. In the first phase, basically you establish a path between the source and the destination. And in the second phase, the actual information or data flows along the established path. Now this information that is flowing in the form of frames, they do not carry any information on a route to take because that has already been established prior to the data flow itself. An important aspect of circuit switching is multiplexing. So basically you need to interconnect multiple switches, and over this link interconnecting between them, you may have to support many conversations. Now, laying down multiple lines will be cumbersome. So your basic idea is to multiplex many of these conversations onto the same single physical link. This is a bit similar to the media access control. So the choices there for multiplexing were frequency division multiplexing, wavelength division multiplexing. This arises in the context of optical fibers, and time division multiplexing, TDM. So let's see how TDM works as an example. Remember, you have only one physical link. So what you do is you divide the time into time slots, and a couple of these time slots make up a frame, and this frame repeats itself. And you allocate a time slot for a given conversation. Now, if there are n such conversations and your overall capacity of the link is R, each conversation gets how much capacity? Right, R over n. In such a time division multiplex system, how do you forward a given frame? So during the call setup time itself, you basically map an incoming port time slot to an outgoing port time slot, and you ensure that the sender sends in the designated time slot. So all a switch does is, when it receives a frame in a given time slot on a given port, it is going to look at what outgoing port this incoming port time slot maps to and sends it out on that particular time slot on the outgoing port. So what are the pros and cons of this particular approach? We covered this as part of TDM. So basically the advantage is that you are assured resources once the call is established. This works very well for constant bitrate traffic. Voice belongs to this category, and that is why telephone networks use this particular switching. The disadvantage is that it can potentially lead to wastage of resources if the traffic is bursty or variable bitrate. Not only that, you need to maintain for a given flow some state in each of the switch, and if the number of connections become huge, like in the internet where we typically deal with billions of connections, maintenance of state becomes a very big issue. Packet switching arose sometime in the 1960s in the context of interconnecting computers. By the time, circuit switching was very well established in the telephone industry. And it was felt at the time that circuit switching is not appropriate for interconnecting computers because the way the computers generate data is bursty with variable bitrate. So there will be a lot of wastage of resources. The world's first packet switch network was the ARPANET, and this is the topology then. All it did was interconnect 4 computers. Notice we are not interconnecting any LANs. Ethernet did not even emerge at this particular time. So these were the machines, these are the hosts, and these were the switches. At that time, these were called IMPs, interface message processors. So the goal of the switch was to take packets from this host and direct it to the other switch based on who the destination is. So here is the first log that established communication between SRI. SRI is the Stanford Research Institute and UCLA, University of California, Los Angeles. The basis for packet switching is this concept called statistical multiplexing. So the idea is, instead of dedicating a link capacity to a given user as is done in circuit switching, let's share the link based on demand. A good human analogy in this context is reservation of tables in a restaurant. So what circuit switching translates to is you making a call upfront and reserving a table, and then you go at the designated time and make use of your table. But often these reserved people don't come, and then the table is just laying idle while you want to have food. That's the wastage of resources. The other alternative, which is packet switching, is equivalent to where there is no reservations. People will come on a first come first serve basis. Whoever comes is directed to a table. You need to take care of a few things in this non-reservation mode. You definitely don't want people to sit at the table even after finishing their lunch for an extended period of time, because you are denying other people who are waiting in line. So this is the fairness issue that is handled by limiting the amount of data. So you don't want to keep on sending very large messages. Instead, you break up a message into packets, and this has an upper limit in terms of size. Thereby, you are ensuring others get service soon enough. Going back to the restaurant model, you also may need to provide a waiting space, because at any given time, all your tables may be full. You cannot predict how many customers are going to come at any given time. This in networks translates to the store and forward operation. So you are getting all these packets and you're going to buffer these packets and serve them on a first in, first out basis. Now, naturally, there is a potential of packet loss because of buffer overflow. In the restaurant analogy, people may wait for some time and then they see that it's too long, and thereby they will leave the restaurant. So let me emphasize these two things. Packet switching is characterized by packetizing a message, that's where packets are coming, and a store and forward mode of operation. So incoming packets are stored and later forwarded on the outgoing link. So the same question as in circuit switching. How do you forward packets to the right port in packet switching? Remember that unlike in circuit switching, we do not have any paths set up beforehand before these packets come. So how do you do it? Basically, in packet switching, packets have to carry some information in the header. This information specifies how to forward this particular packet. How this is actually done, there are different ways: datagram switching, virtual circuit, source routing. We will see all this as part of another video. That packet switching doesn't waste resources is a given. What other advantages that packet switching have? Quite a few. So one is that there is no call setup delay, so a packet can be sent right away. Not only that, there is no per connection state maintenance at a particular switch. There's an exception to this. This is virtual circuits, which is done on packet switching. We'll cover that later. And packet switching is highly fault tolerant. What do I mean by this? In circuit switching, if a switch in between were to crash, that's it, the conversation ends. Whereas in packet switching, if a switch were to crash, the before switch can potentially send the packets, reroute the packets through another switch. So packet switching is highly fault tolerant because there is no state maintenance as part of packet switching. So these are the pros. Can you think of any cons of packet switching, the disadvantages? Well, for one, there is no guarantee for resources. So you may want 100 kbps, but there is no guarantee you'll get 100 kbps. It depends upon how many others are competing with you. Not only that, there's a possibility of out of order delivery as mentioned here. If originally packets went like this and now packets are going like this, there's a possibility of out of order delivery. And there is a per packet overhead. Remember, I mentioned that you need to carry some information in the packet to facilitate forwarding. That's why you have per packet overhead. And the store and forward introduces delays and losses per packet. Buffer overflow can result in losses. And you have to retrieve a packet fully from a link before you can send it out on the ongoing link. So that kind of introduces a delay. So here is an example that illustrates the difference between circuit and packet switching. So in this example, there are users. A typical user alternates between periods of activity and inactivity, and he is active only 10% of the time. In other words, 90% of the time he is inactive. And whenever he is active, he needs 100 kbps. Now, if you were to use circuit switching, what should the link capacity be if you want to support 10 users? Work it out. Well, this is rather simple. Since the activity or inactivity has no role to play in circuit switching, for each of the 10 users, you need to provide 100 kbps. So you need to provide 10 into 100 kbps, that is a 1 mbps link to support the 10 users. Suppose I want to use packet switching now and I've increased the number of users. So typically this can support more number of users. Why? We will see shortly. But let's now assume that there are 35 users in the system. Now each user is only active 10% of the time. So the probability that he is active is only 0.1. Now the probability that 11 or more are active at any time, this can be worked out. I will leave it as an exercise for you, but this turns out to be 0.0004. This implies that with probability 0.996 or 99.96%, you have only 10 or less users active. So if I ignore this case that 11 or more active users at any given time, this happens with such low probability that I'm ignoring it and I'm assuming that only 10 or less are active at any given time, then to accommodate this 10 or less active users, if I were to provide 10 into 100 kbps, that is 1 mbps link capacity, I am done. So as you can see, between circuit switching and packet switching, the capacity is the same. But here I was able to accommodate only 10 users, whereas here I was able to accommodate 35 users. Now it is very much possible that because this probability is not zero, that 11 or more active users are active at any given time, in which case your incoming rate is going to exceed your outgoing rate. Queues will build up and that will result in drop of packets, but that is happening with a probability that is so small that it's okay. Once in a while if it happens, that's all right. So that is the trade-off between packet switching and circuit switching. So here is a summary of what we have learned. Switching helps interconnect host networks in a scalable fashion. We saw two types of switching, circuit and packet, and there are some pros and cons for both these methods. Internet employs packet switching, so we are going to see more of this, the different types of packet switchings involved ahead. Also, when I spoke about switching, I mainly showed how to interconnect hosts, how are networks interconnected. We will see more of this in Ethernet switching, which is also up ahead.